Welcome to another episode of the CarryTrainer Higher Line podcast. Hey guys, welcome to another episode of the CarryTrainer Higher Line podcast. We've got an interesting one today, a physicist, Mr. Andrew Dotson. And that's the name of your YouTube channel. It's just your name, right? Not just
Yeah, that's correct.
It's not like the physics guy, it's Andrew Dotson.
No, all those were taken.
Okay. So you're like, screw it, I'll just go with my name.
Yeah, I mean, my buddy, he had a good point. He was like, you can either try to market a brand or you can try to market yourself. So I figured having my own name as the title was a pretty good move. So
I dig it. You and I had a conversation a couple of days ago before we got this on the calendar, just chatting a little bit. Tell the listeners a little bit about yourself and why you started what has become a pretty successful YouTube following, Talking Physics.
Sure. So I am in my third year of a PhD program in theoretical nuclear physics. I started out as a biology student, realized that really wasn't for me. And I've always enjoyed entertaining people. And one of my best buds, he had been trying to get me to get onto YouTube for quite a while. And eventually once I made this change over to physics, I realized that it wasn't all of the representation on YouTube were people who were going to Oxford, people who went to Harvard, and were like, here's what it's like if you're someone who goes to Harvard. It's like, okay, that's a very niche group of people, I'd say, but maybe there's a market for the normal student that wants to go and study physics, or do you have to be some genius to go do it? So I thought maybe there was a market for that. I started recording myself going to and coming from classes and the interactions throughout the day, getting my undergrad degree, and people started watching. So eventually, go ahead.
Let me jump in. What the heck is theoretical nuclear physics?
So first off, what is theoretical physics? And then we could talk, I guess, about the nuclear side of things. If you think about it, I'll probably paraphrase Richard Feynman a bunch of times throughout this video. He was like the physicist. We are at the end of this 400 or so year journey in physics of a very effective means of figuring things out. You know, having an idea, testing that idea. If it doesn't work, change your idea or keep going with it, keep testing it. And it's not perfect, but it's gotten us to where we are today. And a couple 100 years ago, 100 years ago even, you could really be a jack of all trades. You could be the person who's out there having the idea and conducting the experiments, doing everything yourself. You'd be doing all of the math, you'd be doing all of making the experimental equipment, making the measurements. Nowadays, that's not very practical. That hasn't been practical since at least probably World War II era. They say Enrico Fermi, you're Chicago, you know Fermi Lab. He was the last of a dying breed of physicists who could wear both hats of being an experimentalist, the person who would go out and do experiments, and a theorist, the person who would create the mathematical framework that we think describes how the physics, how the natural world takes place, how it behaves. So there's two schools of thought. There's the one who makes the predictions using the math, and then there's the people who test the predictions through experiments. So you get the theorist and the experimentalist. Now I do nuclear physics, so I'm pretty much strictly interested in protons and neutrons. If I widen my scope to more other kinds of particles, I may call myself a particle physicist. Really depends on who I'm talking to. But I think that's all there really is to it. Are you more interested in studying the math, or do you want to get your hands dirty and make some measurements?
So you're a math guy.
Yeah.
Why do physics, or the study of physics rather, let me rephrase that. Why does physics matter? Why does it matter to the people listening? Why does it matter to average people? Does it?
It matters. I think that it matters because you can always ask why something works or why something happens. Try to explain a phenomenon. And then if you keep asking why, eventually you lead to the physics. You can ask about biology. You know, why do cells behave the way that they do, or if you have certain ions in your body, why do they tend to go towards a certain direction? You can go from the biology, you ask why, you get to the chemistry. You ask why the chemistry, you get to the physics. Why does chemistry work? Physics was what turned chemistry into a real science. Before that, it was just, this is what this element is. This is what this element is. And then quantum mechanics comes around and gives us an explanation for why the periodic table is displayed in a certain way, why it works this way. So long as people continue asking why things work, you need physics. The one big thing is, when it comes to a fundamental science like physics, and you're doing fundamental research, it can be incredibly difficult to say immediately what your research will be used for, right? If you're looking at something or attempting to answer a question that hasn't been asked before, hasn't been answered before, you're also probably not going to know what practical application it's going to immediately have. But the good thing about physics, and especially nuclear physics, is that the track record is what you could point at and say it always is eventually useful for something. You know?
I gotcha. So when you and I started talking, you follow our stuff, I follow your stuff, and I'm not a physicist, I'm not a scientist, but what I love about science is it's quantifiable. I'm not explaining this to you, but just talking about like why I enjoy science. Like it's not open to interpretation, right? You can, it is and it isn't. But where I'm going with that is why I enjoy it is it seems like if more people understood why and how sciences work, we might be able to like communicate better, maybe get a better dialogue going between political parties, religious ideologies, etc., because we start to look at the natural world and break it down into what it really is and why, rather than how we feel about it.
Yeah, I couldn't agree more with that. That's definitely the direction we'd like to think of ourselves as heading down. But physicists, scientists as whole are still people. We all have our own biases, and we have our theories that we cling on to, and we may like to think that, given an idea that is contrary to what we already believe, if it agrees with experiment, we would just drop the old theory with the drop of the hat. But at the end of the day, everyone is still a person. I think scientists may be more effective and less partial as a whole, but I think it's a work in progress for everybody. But what I like about physics is, so I said that I started out in biology, and just in my experience with the coursework that I had, it was a lot of, this is what this is called, and this is what this is called, and this is what this cycle is. And it just wasn't very satisfying. It just felt like a lot of bookkeeping, like stamp collecting, just
memorization. And
a lot of memorization, exactly. So physics just seemed like such a great way of, it was more satisfying. You could explain the process and you could make other predictions on top of that, which was like, okay, cool, this is better for me. This is more in line with how I think.
Were you a genius in grade school and high school?
I was not a genius in grade school, in high school, and nor am I a genius now. I was a C student in high school. My first semester of college, I got a D in English. It's just it's a matter of priorities. I mean, I'm in grad school now. I think with all of the courses that I've taken, I've gotten 1B in grad school. It's just, what are you really interested in? Like if I think I talked to you about this when we spoke briefly before, where with physics for me now, I don't really have to rely on the willpower to like get my shit done and get my work done and study. It's more of something that's pulling me towards it rather than having to push. So if you can find that thing for you, whether it's physics or whatever you're interested in, it just makes it so that it requires less discipline, I suppose. Because I'm not any smarter than I used to be. I'm just,
when you run into people that you grew up with, schoolmates, teachers, people from town, because you live across the country from where you grew up now, right?
Right.
And people hear what you're doing, what do they think? Or if people see you online, like, wait, Andrew has a huge YouTube channel on physics? What the?
As far as old friends and stuff go, I tend to keep it to myself. I don't really post about it on Facebook or anything. I have my YouTube community and I post things physics related there, but I'm not too big on social media. So I would say that most of them probably don't even know.
Okay.
I think they would be surprised that I went the physics route because it seems like it kind of came out of nowhere. But
So you and I, when we were chatting, well, we talked a little bit about what I do, ballistics, things of that nature. Let's chat about that and how science in the physical world kind of correlate into shooting, firearms, things of that nature.
yeah, there's definitely, you hit the like right on the head there. It's all ballistics. I mean, you could think that you could just start asking questions about how guns work, and it all comes back to physics, I suppose. Like you could say, why is there seemingly less recoil in a semi-automatic pistol as opposed to one that you may manually have to bring the hammer down each time or rack the slide before it fires? Like two guns, exact same size, but one's semi-automatic and one is not. Why does the semi-automatic one have less recoil? Or why does it tend to? And it's because that force from the gun, you have Newton's laws. You have every action has an equal and opposite reaction. So you have the force on the projectile shooting it out. That projectile has an explosion that's pushing back on the gun. And if you have that explosion that is taking place, it's exerting its force over a longer period of time, you'll experience less recoil. So you have the bullet that explodes, or sorry, it doesn't explode. You hit the primer, then you set off that reaction, and it's pushing back on the slide rather than having this perfectly rigid gun that has to feel all of the force. So it pushes back on the slide. So some of that force is used instead of being used for recoil. It's used to help chamber the next round, right?
Getting dumped off to cycle the machine. Here's a good one that you can add some insight to. So a lot of folks feel that heavier bullets of the same caliber have less recoil. So 115 grain bullet versus 147 grain bullet. I do not agree with that. I say a heavier bullet has more recoil, but there's a lot of guys that say a heavier bullet has less recoil. What do you say about that?
I'd have to think about that one for sure. So the thing is that the reason I have to think about that is you can have two bullets that have the exact same momentum, but one may be traveling faster and it has a smaller mass, like if you have a smaller grain bullet, or one may be heavier but be traveling slower, and they could have identical momentum. So the first thing is can the targets or can anything tell the difference between whether, if they have the same momentum, how can it tell that the lighter bullet or the one that's traveling faster, that the target knows that, like, oh, I should brake when that one hits me, but not the heavier one? Like there's this question of how does momentum affect these things? But the force of recoil isn't necessarily due to the momentum of the bullet. It has to do with how the momentum is changing, how it's going from 0 to whatever speed it has. So a changing momentum over time is what the force is. So if you have a projectile that changes its momentum over a shorter amount of time, that's going to be identical to having a much higher perceived force. So I suppose I could see like a smaller projectile having an equivalent recoil because the momentum changes. It may accelerate a lot faster because it's a smaller mass. You don't have to push it as hard to reach that velocity.
Interesting stuff. If I fire a gun straight up in the air, will that bullet come down and just destroy buildings?
If there was no wind. So there's, well, I mean, not buildings per se, but
don't answer this. I'm just playing. Don't answer this. So you started a YouTube channel. You've got, what, 170 or 80,000 subscribers. What do people come there to learn from you? Are all of these folks on the same journey of physics? Or is there laymen that are there just looking to learn about how to understand the science? What do you do different than other people in that space? What are you passing on to folks?
I think the only contribution or unique contribution that my channel kind of offers, one, I try to take a more comedic approach to everything, whether it's an actual lecture or a dedicated skit just kind of poking fun at things. I try not to take it too seriously. It's easy enough to steer people away from science, especially if you can't crack jokes. There's also, it's an interesting time because there's no shortage of popular science communicators nowadays. Right? There's tons of resources of people who will go out and tell you all of the cutting edge stuff that we know of in physics right now. People talking about string theory, people talking about dark matter, black holes. And it's these very surface level explanations that get people interested in science. I think that has its place. I think it's great that people do that. But there's no place for me in that. Right? It's already saturated enough, I'd say. There's plenty of people who are way better at explaining the surface level stuff and having the great analogies that I don't really think of. And then on the other side of things, there's the completely formal lectures that you would have to pay $1,000 to go attend in a university, and then you have your homework and everything. And it's the opposite. It's like if you're someone like me who kind of got interested in physics from those popular science communicators, then you actually get into your physics degree and you're like, excuse me, this is day 2 and we haven't talked about string theory once. All we've talked about is friction. So there's there's this gap between the cool, sexy stuff in physics and what it is actually like. And there aren't too many people communicating what your experience would actually entail. I think part of the appeal is that I show what it's actually like without taking it too seriously in the process.
I like that. I like that there is a couple 100,000 people in the world interested in learning about physics online. I mean, I think that's pretty freaking cool that how many niche, not that physics is niche, but niche social media channels, which is what YouTube is, that you can pump this content out there and there's multiple hundreds of thousands of people looking to consume that kind of information. That's pretty rad that we live in a world that you can do that, especially in your free time.
Yeah, it's I never would have thought there'd be this much of a market for it, but it just goes to show that there is a way that you can present this information and it doesn't scare people off. You just have to get a little creative with it, you know?
We get a lot of, not a lot, but we get our fair share of people challenging, some hater type people. Do you get any of that? Like, is there like a weird vibe in the science community? People like, Andrew, that concept's bullshit. Your science is junk.
For the most part, everyone is very respectful. I can make mistakes, and I've made mistakes on videos where I explain a concept. Maybe I have a typo on a line of an equation, and people are like, "Oh, I think that this should actually be such and such," which is always that's something that should be encouraged. I don't know. You could take a critique to heart without taking it personally. It's not an attack on your person if you actually do something wrong. I do get my fair share of emails, though, that are the people who say, "Hey, I just want to let you know, I saw that you made this video on relativity or you made this video on quantum mechanics. I've proven it wrong." Not me, the people who are emailing me, they'll say, I've proven it wrong. I don't know if you want to take your video down or if you want to talk or what's your phone number, and I'll tell you how all of this stuff is bullshit. And then they'll follow it usually with, "I don't know the math. I was hoping you could help me work it out."
So I disproved a widely accepted belief, but I can't tell you how I disproved it.
Right. Like this notion that you can disprove, well, I shouldn't say that. You can certainly disprove a theory by providing experimental evidence that isn't in line with the predictions of the theory.
Right?
Right. But to say you've disproved it with like a little half of a thought, because what they'd be suggesting is that they have their own line of logic, and when they go from point A to point B in their logic, the theory has somewhere been disproven in that line of logic. But that's all that math is. It's a succinct way of expressing the logic. You can write one equation, or you can write a paragraph in words describing what that equation is telling you. So these two things aren't disconnected in any way. Logic is math. So to say that you come up with a logical argument and you don't need the math to show it, that's kind of silly to me.
How do you respond to these people?
I usually don't. I'm not the most patient person with that kind of thing. And I also don't want to hurt anyone's feelings. So I know sometimes I'll get an email like that, and in my mind, I'll if I were to respond right then and there, I may come across mean. So I'll say, okay, let me take a breather. Let me not respond to this right away. I'll come back to it. And then eventually then I'll get 5 more by the time I'm ready to come back to it, saying the exact same thing. And I just don't particularly have the patience. If enough people have this misconception, I'll make a video addressing the topic without singling anybody out, though.
And
As an example,
when you make the video, do any of these people ever comment or email you again, continuing their challenge of the science, or do they fizzle out?
there may be a bad explanation in my video that maybe didn't hit the driving point home well enough. So someone may comment and be like, I kind of see what you're saying, but I don't understand such and such, in which case I'll address that in like the comment section. That's another great thing about YouTube, is the dialogue you can have with the people. It's not just projecting out some material to the world and then moving on. It's like putting stuff out there, and you can have a back and forth with the people who are watching it. I think that's what makes it so much, I suppose, more promising than maybe watching television or something. Because it actually does feel like a community.
I was hoping, and we're starting to talk about it a little bit, what I found so intriguing as we were discussing doing this was just kind of the dive into the human condition. The fact that in the world I'm in, the world, I've got friends that are professional chefs. I mean, if I put a video up showing me making an omelet, I will get 10 private messages telling me you did it wrong and here's why. And it's like, first of all, asshat, I didn't ask your opinion, nor did I tell you this is the only way to create an omelet. You know, this is just me doing whatever I do. And actually, I kind of know what I'm doing when it comes to some of that stuff. But again, do whatever you want to do. But it's interesting. It could be cooking, it could be shooting skills, or it could be science. We humans are so quick to not only properly consume information for what it is, like there's nothing you put out that says, I am Andrew Dotson and everything here is the law, right? Like, this is my opinion. It's me having fun, putting my stuff out in the world, take it or leave it. But people will go out of their way to be contrary and create controversy and argue. Like, I'm not a scientist, so I would never step into that space and say, well, I've disproved the theory of relativity or any other thing, because I'm not intelligent enough in that space to have even that argument. But then even if I was, why? Like, why? And then why doesn't that person go ahead and craft your own content proving your belief system? But folks don't do that.
Right. That's something that I struggle with, because there's I think everyone should be open to critique in some way, right? Like, if someone says what you're doing, if I'm solving a problem and I have the luxury of broadcasting the way I solve a problem to a bunch of people, and someone comes along and says, you know, you're scratching your left ear with your right hand here, like, yeah, you can do it, but that's not the way. That's not the best way. There are better ways of doing it. If it's a better way, then that should be addressed, right? I don't want to teach people bad habits or teach people inefficient ways of problem solving. So I hope what people take away is there's a bunch of ways to solve the same problem. This is just how I thought of doing it. I typically don't come across that very much when I solve a physics problem in a video. The only times I really see that are if I do a video doing coding, because a lot of what I do in theoretical physics, it's either impossible or very inefficient to try to solve the problem on pen and paper. you'll typically write a computer code to solve the problem for you. And I'll get a lot of criticism on the way that I wrote the code. Like, it's like, that's not the efficient way of, you could easily have parallelized this code and had this core solving this problem. And it's like, okay, dude, like, I'm not a computer scientist. I understand that there's better ways. I think everyone understands that there's better ways. There's just, when it's a matter of taste or a matter of like, yeah, here's just one way of doing it, and you're not trying to pretend like there's not other ways of doing it, then yeah, I can see how that's a bit frustrating. But I think we should always be open to better ways, or someone commenting saying, yeah, this is actually not the best way of doing it. This is probably more harmful, you know?
As I'm listening to you, that's the takeaway for me is from your perspective or mine as the channel curator, or for anybody, you said be open to critique. Like that, if we are trying to grow, my goal isn't to create a bunch of YouTube videos. It's to grow in my space, not grow followers, but grow as a human. If you're not open to critique, then you're not open to input, which means you're pretty closed off. And like, again, that's why I like science. It's not subject to people's feelings or emotions unless they make it so. Like religion gets in there constantly. Well, that can't be real because this holy book says otherwise. Yes, but this set of experimentation, that we can quantify and repeat over and over doesn't agree with your holy book. And I'm not knocking anybody's holy book, but that's like the feelings and open-mindedness. I can't open my mind though, because this holy thing that I agree with says that experimentation must be witchcraft or some other type of sorcery. So it like in this, like for myself, I've grown a lot using social media, and I will continue to. It's a challenge at times to not be like short-tempered or dismissive, because sometimes it's like, yeah, even if that person's opinion, that if I don't agree with it, I guess had I thought more about my presentations, they would have understood better. Like that could be the takeaway for myself or you, which I think you kind of said.
Yeah, I think you put it better though. There's definitely a stage with everyone, at least in science, where you start to really see a lot of examples of you not knowing what you didn't know. And there's the sense of humility, I think, that comes along with that. And until you get to that point, you may just be tempted to call bullshit when you really don't have enough of a background to do so yet. And I think it's just on us to be able to handle that situation, hopefully in a diplomatic way. I mean, you understand, like, people, if you don't know how often you can be wrong or how many more exceptions there can really be to a rule or how many details are overlooked or not addressed in a video, then you don't know to look out for that, or you don't know how your own intuition may be failing you. And as long as you understand that about some people, it's easy not to get super worked up, I suppose.
The challenge is that's many people.
I'm very lucky then, because the people who watch my videos tend to be, they may disagree, but they always do it in a respectful way.
Well, yeah, it's freaking physics. It's a physics channel, all right? I mean, you got a bunch of brainiacs on there. How long have you been doing the channel?
Coming up on 4 years, I think.
That's pretty awesome that you grew that big in 4 years. Well, we've got a lot of content developer, creator people that follow this podcast in various sectors. Talk a little bit about that, not just from the content, what you're creating, but you're a full-time student, which I'm sure is a big workload. How do you manage creating content, editing, uploading, responding, and so forth with comments and all that jazz?
So, I mean, I've said it a bunch of times on my channel. I am a physics student. I'm a PhD student who also makes physics videos, not the other way around. So if I have a project, like a research project that I'm working on, or if I have big things coming up with research that need to take priority, I don't lose any sleep over that. YouTube will always come second to me. I just enjoy being able to tell the story along the way. And if that story has to be told after the fact so that I'm not compromising the quality of my work, then so be it. And I think people, when I first volunteered that information, I think I was kind of nervous about how that would be received from the people who were watching my videos. And luckily, I think that made people like them more. People understood that I wasn't just here for YouTube. Like, that wasn't necessarily, it's one of the passions, but the priority will always be the physics. I used to, so a little bit of a backstory. When I got my physics degree and I started applying to graduate schools, I didn't get into the one that I'm at immediately. I was actually rejected. So they put you on a wait list if you're close, but they're like, let's look at how the better people, if they accept our stuff first. They may put you on a wait list, and then I was rejected. At the time, I had upwards of like 10,000 subscribers, and my girlfriend, who's doing a PhD in astrophysics, got in. So I had gotten into other schools, but I knew that I wanted to come here, one, because she came here, and two, because they had diversity in, as far as, it may sound weird, but there's a lot of different branches of nuclear physics that you can go into. And the school offered more options. So I was like, it's kind of a win-win. I didn't get in, but I can always reapply. So what I ended up doing was I made the decision to move out here to New Mexico anyways, and I paid to take classes as a non-degree seeking, PhD level courses as non-degree seeking, in hopes that if I was on their own turf and I was interacting with the professors, they would see that I had what it took to be in their program. And thankfully, it ended up really paying off. But at the time, so since I was just paying to take classes, I still had extra time, and I wanted to grow the channel as well. So I started doing these daily uploads. I would make a new video every single day. And as those days went on, I started developing more and more of a following. And the way that I rationalized taking the risk of coming here was I said, okay, if I offer a tutoring service in physics, like via Skype or something, and I advertise that to my YouTube channel, then maybe some people would be interested in that, and maybe I can support myself that way until I get into the PhD program. And just enough people did. Just enough people, signed up for the tutoring so that I was able to financially support myself. So it was a very big risk, but in my opinion, this was the only time in my life where I could take a risk like that and it not affect other people. I'm a guy in my 20s. I don't have kids or anything like that. Like, it was a big risk, but I figured if there was a time to do it, it would be now. So at that time, I was making these daily uploads, and I didn't know, I saw that the subscriber count was going up, and I didn't know what would happen if I stopped, when I stopped, because I knew that once I got into the PhD program, then I would have to also be a TA. I'd have to be a teaching assistant. I'd have to be doing research and all of this other stuff, and there just wouldn't be the time to do that. So that was a very nerve-wracking period of time of like, what happens when I stop? And thankfully, everyone has just been on board since the beginning. So I have a lot to be thankful for in that regard.
How long did it take for them to accept you into the program?
1 semester. So I took 1 semester worth of classes and took a few physics classes. And then I retook one of the standardized tests that I did poorly on, that you send out to all the grad schools when you're applying. It's called the Physics GRE. And so after getting all A's in those classes and doing better on that GRE, then they let me in.
Awesome. There's a lot of good lessons there for listeners on persistence and keeping after something that you're passionate about and want to do. And I think too often we give up when something doesn't go our way or is more of a challenge than anticipated.
Yeah, I mean, I'm definitely not saying, yeah, if you didn't get in, don't take responsibility and don't change anything about yourself and take the risk anyways. Like you gotta be honest with yourself. But yeah, it ended up working out for me.
I think there's a lot of easy lessons that we skip right by because we are more interested in the quick win, the path of least resistance, as a lot of people put it, and like in the sense of developing the social media following, which you can use that, dovetail that into a lot of various into a lot of different good in your life, as you already are. And there's just tons of lessons that from production to management to communication to teaching that you're teaching yourself in the development of that. I think people that listen to this podcast and others like it that are looking for inspiration or ideas or concepts for growing and developing stuff. There's so much that you've just done in this short 4 or 5 year time frame. It's really cool. What do you plan to do 2, 3, 5, 10 years from now? Do you still see yourself running that YouTube channel?
That's the goal, man. So the way that the path generally goes, so I'm doing a PhD because I want to do professional research. And if you want to be a research physicist, you have to do a PhD for the most part, especially in theory. So the path generally goes, sorry, that's my cat. The path generally goes,
Stop.
She says she's here. The path usually goes, you get your degree in physics, then you go to a grad school and you do your PhD. In America, you don't have to do your master's first before doing a PhD. You can jump right in. Then after you get that, you do what are called postdoctoral positions. They're temporary research positions, typically at a national lab somewhere, where you're building up your resume and you're doing a certain research project for 1, 2, 3 years, and then you apply for another one. And you lather, rinse, repeat that process until you get a full-time faculty position somewhere, whether that be at a national lab as a staff scientist or maybe at a university if you're lucky. But that'll be the path that I end up following. And there's really no templates you can look at for what that's like or what you can expect. So that's the goal, is to be that resource.
Is there certain problems or concepts or ideas that you're hoping to spend your life working on or solving or digging into?
There is one. There's this really interesting property in quantum mechanics that's referred to as spin. It doesn't have anything to do with the particle spinning. It's horrible terminology, but it's just what's persisted.
How old is this term?
It's since probably the 20s or 30s.
Okay.
So basically, when quantum mechanics started, you had a man named Schrodinger who, there's this wave-like nature of particles, and if particles exhibit this wave nature, then they should obey what's referred to as a wave equation. And when you follow that down the line, you get to what's called the Schrodinger equation. And unfortunately, it wasn't compatible with relativity. So what I mean by that is it was a theory that could describe the electron. Everyone's probably heard of electrons. They're the fundamental particles that have negative charge. As long as it wasn't traveling at like very high speeds towards the speed of light. When things start moving that fast, you have to incorporate relativity into the mix. And there wasn't really a way of doing that yet until another physicist came along. He's the most famous physicist you've probably never heard of, known as Paul Dirac. And he was the one who figured out how to unify the two, quantum mechanics and Einstein's theory of special relativity. And you get this phenomenon known as spin that falls out of the theory that all quantum mechanical particles exhibit, and no one really knows where it comes from. You can't do quantum mechanics without it, but if you have a proton that has spin, and protons are made up of quarks and gluons, you say, okay, how do you get the spin of the quark from the particles that make it up? And no one knows the answer to that question yet. So I'm using the word a lot. I should try to explain what it is. What they did at one point is they took this, you could think of it as a container full of silver atoms, and they formed a beam out of them. They heated them up so that they had a lot of like random motion in the container, and they directed a beam of those atoms through a magnetic field, and they were basically studying how do those beams of silver atoms get deflected. Since the motion was supposed to be random, they expected to see them deflected in all kinds of directions. But that's not what happened. Like if it's completely like random, then a particular quantity could take on any value, and when it interacted with a magnetic field, it could be deflected any which way. But what they observed instead was they directed that beam through, and it was either deflected up or down. Nothing in between, which was particularly weird. So they referred to this, what this thing was related to, as quantum mechanical spin. So for an electron, it can have spin up or spin down, which refers to the direction that the particle would be deflected if you throw it through this magnetic field. For other kinds of particles, they can have different spin, but it's a very complicated thing to try to explain because it has no classical analog. You can't say, you could think of it as this thing that's more familiar to you. There's not really another example like it, which is why people like myself have such a hard time explaining it. But it has to do with magnetic properties of the particles, and how you get these properties from the quarks and gluons that make up the proton is an unanswered question. And that question fascinates me. So it's a very technical question. I get that I'm probably not doing it any justice. There are good ways of explaining it. I'm probably just not doing one of those ways. But that's what I'm really interested in, is how the proton gets its spin.
So that is what's so exciting about science, is how many things we don't know and understand. And so many people, I think, just assume that we have answers for everything. You go to the doctor, they give you a pill, you're okay. Not even close. Not even, like, there's just so many things that we're not even close to understanding. And what you just talked about is another one of those amazing bits of our universe.
Yeah, I think it's pretty fascinating. There's another project that I'm deeply invested in, which has to do with, you have these little quarks and stuff inside of the protons and neutrons, and they're moving around, and how is pressure distributed inside of that object is also an unanswered question. So yeah, there's a lot.
How do you answer it?
So,
like, how do you even approach that problem?
It turns out that the way that you can probe these kinds of questions is using particle accelerators. So what you end up doing is you have a target, something that you're interested in. Like, it could be a bunch of protons, like a target full of hydrogen or something like that. And you direct a beam of particles, like electrons, at that target. And you see how the beam of particles deflects, like where it ends up going. And you're just counting how many times it went over there, how many times you measured a particle over there, or how many times you measured a particle over there, and so on. And what you end up probing when you do these kinds of experiments is you understand the nature of the forces that are at play. So if you're shooting electrons at charged particles and you're looking at how they're deflected, what you're really measuring there is the electromagnetic interaction, the electromagnetic force. So in designing these experiments to probe the target in these various ways, you get insight into the fundamental interactions of nature, and how you construct, or how you set up the experiment, like set up the certain properties of the target or the beam. You can look at different things also. So as an example, if I had like this weird object and I directed a beam of charged particles at it, I would be able to measure the distribution, the charge distribution, by doing these kinds of experiments, assuming that the target that I'm hitting is made of stuff. It's not like a fundamental particle. So it all comes down to scattering experiments. That's what the experimentalists would do, right?
So it just requires somebody to sit down and create or craft a experiment, and if it works, great. If not, craft another one and just keep doing it until the data points exist.
Yeah. So the famous saying is theory guides, experiment decides. So if you go to government, if you go to Congress or something, and you say, I'd like funding for this new particle accelerator, we want to smash some particles together and see what happens. It'd be like, okay, great. What are you going to find? Or what do you hope? What are you going to see? If you were to come to them with saying, I don't know, we just want to smash these particles together and just see what happens, that's not a very good answer. So you need the theorist to come along and say, this is what we expect to measure. This is, if we're hitting these protons together, we expect to generate maybe a Higgs boson, and we'll find it at this energy. Like, make these predictions so that you're not saying, let's just have a whole range of energies that will span through and we'll need for this particle accelerator. If we know that the Higgs should exist at this range, then you're cutting out a lot of the cost of the other ranges and things like that. So there's this delicate dynamic between the engineering and the experimental side of things, of actually making these colliders, and the theorists saying this is what we expect to measure in the first place. So yeah, that's about it.
Toss some information out for the lay person like myself or others about why we should give a shit about physics.
I think it was Michael Faraday. He used to do these really nice demonstrations, these really cool demos, back when electricity was first being sort of understood, at the time of Maxwell and all of them. And he would do these really cool tricks. And one day someone came up to him and said, Faraday, these are really cool tricks, but what the hell could you ever use electricity for? Where's that ever going to find practical use? And he said, I haven't the slightest idea, but I promise you one day you'll be able to tax it. That's the track record of physics. You never know what it's specifically going to be used for, but it's incredible that it always is used for something. As an example, if you slap a magnetic field, or if you slap neutrons with a magnetic field and they start processing, it turns out that understanding this mechanism is exactly what you need in order to truly understand how things like an MRI work. Nuclear physics in particular, you can always point towards medicine to say, understanding this stuff at a more fundamental level, even though it just seems like a who the hell cares kind of question, it always has some kind of practical use eventually. When Dirac, I mentioned him earlier, in his famous Dirac equation, it predicts the existence of a very exotic kind of particle known as the positron. It's the antimatter version of the electron. And this isn't just conjecture. It's something that we can actually measure now. We understand that they have to exist, these anti-electrons. Now, if you think about, cool, more kinds of matter, there's the zoo of particles. What the hell would you use positrons for? That's literally what the P stands for in a PET scan, positron emission tomography. They use these kinds of principles to either make very precise measurements, because if things annihilate, the energy that will be produced, the photons that are radiated, will be radiated with a very particular wavelength that you can manipulate, and you can shield different areas of the body so that you're hitting parts of the tumor that you want to hit and you're leaving other parts alone. This all comes from having a fundamental understanding of how nuclear physics works. If you can't make these predictions because we're not asking the fundamental questions, then you can't have advances in these innovative branches in modern medicine. So
very cool.
Yeah.
That's a nice connection. How far do you think things will go in our lifetime?
In our lifetime, I think fusion is reasonable. I'm not the most well versed in that and how it works, but it seems like nuclear energy coming from nuclear fusion is something that could happen within our lifetime. But they've been saying we're 10, 20 years 20 years ago, they said we were 20 years away from nuclear fusion. 20 years before that, they said we were 20 years away. So I'm not sure how far we actually are, but that would be pretty cool to see. So I'm picking on nuclear physics. Do you have any, are you asking about that? Or are you asking about?
I guess in general, I mean, I'm not a physicist. You are. But, I mean, I think looking at things like flight 100 years ago, it was pretty absurd to think about things flying at the speed of sound, and now we fly far beyond that. There's so many massive advances that in how we are manipulating matter in our universe. It's crazy.
So what's interesting, that's a cool example that you bring up, the speed of sound, because then you say, oh, physicists say we'll never travel faster than light, but we used to say that we'd never fly the speed of sound. Before that, we'd never even fly to begin with. But those are things that we actually still observed at the time, right? When people said we would never be able to fly, there were still birds. It's not like birds were invented after the fact. Like, we could see that some things, nature figured it out in front of us. It's just that we're too stupid to figure it out at the time, but it still exists. If we were to talk about the speed of sound, you have bullets that travel faster than speed of sound. You have the bull whip. The sound of that cracking is breaking the sound barrier. So these things already existed. We just didn't know how to replicate it by ourselves. We weren't innovative enough to do that at the time, but the phenomenon, there was nothing preventing it. Something like traveling faster than light, however, we are asserting that is fundamentally impossible.
You still are.
Yeah, and that's something,
because nothing goes faster than light, or because
the issue here is that nothing can accelerate to the speed of light. Nothing with mass can you start speeding it up to exactly the speed of light. There's actually not really anything prohibiting objects existing faster than the speed of light. But by definition, we just wouldn't be able to measure them. If you're a Star Trek fan, that's like the whole concept of a tachyon. There are these particles that exist faster than light.
You just dorked out so hard.
Yeah. You're talking to a theoretical physics person. I don't know what you expected. But yeah, the issue has to do with accelerating, because when you accelerate something, you're fighting against its inertia, right? An object in motion will stay in motion. And if you try to accelerate it any which way, you have to apply a force to do that. It turns out to accelerate an object, the faster it's going, the more inertia it has. So you have to constantly be pushing it harder and harder in order to accelerate it faster and faster. And you would need an infinite amount of force to accelerate it to the speed of light. So
did I actually hear you do a video on this?
I've talked about it a bunch of times, because there's a lot of misconceptions about special relativity. Is one of those things. That's what this has to do with, is relativity. Unfortunately, it's often taught by people who don't work in relativity. So they give you a lot of false information or a lot of misleading information. They'll tell you things like mass depends on the speed of light. Or sorry, mass depends on how fast you're going. Like, if you are going faster, you somehow are made more stuff or something, which is not correct.
I've heard somebody say that. Like, go ahead.
Mass is defined as how much energy you have when you're at rest, times c squareds, right? E equals mc squared. So your mass is in your own rest frame. You who are never moving relative to yourself. You can be driving down the car, but if you look at yourself, you're still stationary, right? It's everything else that's moving relative to you. Mass is defined with respect to how much energy you have standing still. So if you start going when you're not standing still, we'd like to be able to talk about that as well. I'm paraphrasing Sean Carroll here, who's a famous physicist. He said, if you're moving, we'd like to also be able to refer to that kind of energy. And what should we call it? Well, we should call it energy. There's still kinetic energy, energy of motion. But what, some geniuses back in like the 60s decided to do was they invented this term. Instead of calling that energy still, they called it a relativistic mass. And it's been confusing physics students ever since. So if you talk to the general public, I think most people would say mass doesn't depend on how fast you go. If you talk to a physics student in their first or second year, they may now be tempted to tell you mass depends on how fast you're going. And then if you, again, talk to someone who works in relativity, then it's going back. It's like, no, it really doesn't matter. That's one of the things that really frustrates me is how many people are teaching people the wrong thing with relativity there. But
teaching the wrong thing?
Yeah, so they're giving people the wrong impression that mass depends on how fast you're traveling, and what it comes down to is, I mentioned the word inertia. It's an object's tendency to resist accelerating in a certain direction. Newton's laws, it's permissible to treat the mass of an object, as being the inertia of the object, because F equals ma. The more massive it is, the more force I have to apply to accelerate it. So people in everyday life, that's why I said the first year physics student may make this mistake, is because we associate mass with inertia. Once Einstein came around, he showed us that it's not just the mass, it's the total energy of the system that contributes to the inertia, which has to do with its mass and how fast it's going. But how fast it's going has to do with its kinetic energy. It has nothing to do with its mass. But if you have people who don't work in relativity writing physics books and have to introduce people to consequences of special relativity, oftentimes they use this terminology, relativistic mass, which is just, I mean, you can define things, you can call things whatever you want, but if you're teaching it to someone who doesn't have intuition for this stuff yet, they're going to move forward through their physics degree with the wrong impressions. So that's, I think relativistic mass has to be banned.
You hear that, people?
Actually,
you hear
no.
That?
I'm very against censorship, but I think people should volunteer to not use that terminology anymore.
So what you're saying is you think bad science should be proliferated if people want to.
I think people should have the right to say whatever they want. And I would like, people can have opinions about whatever they want. It's just, I would like people to make sure that opinion is educated. But I'm not going to force people to do one thing or another.
Yeah, don't hold your breath on that, Mr. Dotson. Don't hold your breath on that.
Wishful thinking.
Yeah. Hey, I appreciate you taking the time to chat with us, bro.
Yeah,
I'd like
absolutely.
to ask people. Thank you. I look forward to seeing what comes out of your channel the next couple of years as you go deeper into your PhD. I like to ask people that visit with us, if you never get to meet the people in person that you chatted with today, what would you leave them with? What would you have them remember you by or for?
If this is something that you're interested in, if something like physics is something that you're interested in, but you've been convinced by other people that it's only for the geniuses out there, I think I'm a living example of that not being the case. I'm someone who, there's nothing special about me. I never was like the straight A student or anything like that. This is something that can absolutely be learned and be mastered by, I think, anybody, so long as you have the interest. So I think that's the main takeaway, is this is really something that anybody can get a hold on.
I like that. How do people find you online?
I'm really just on YouTube at Andrew Dotson.
Spell that all out just so they can punch it in and find you.
It's Andrew Dotson, so everyone knows Andrew, but Dotson is Dotson. You can find me there. I'm not on Twitter really or anything else.
Just the YouTube. Well, it's the second largest search engine in the world, so you picked a good one.
Yeah, man.
I appreciate your time, man.
This was great. Hopefully we can do it again sometime.
Yeah, I'd love to. Talk some more ballistic stuff. Maybe we'll get you out onto the range with some high speed and have you do some calculations.
Yeah, man. Don't threaten me with a good time.
That'd be fun. You guys that watched or listened, depending on where you're at, we appreciate you. If this is something that you found interesting, if there's ideas or people that you think would be cool to have on, please shoot us a message to training@CarryTrainer.com. If you like these podcasts, hit the like and subscribe button. If you're checking this out on YouTube, share them with people on your social media. And as always, don't be dickheads. Tell somebody you love them. That's all I got for you. Bye.
Visit our website, CarryTrainer.com, for information about classes held throughout the U.S., CarryTrainer apparel, and upcoming projects. You can also email us at training@CarryTrainer.com for information about setting up your own private course or speaking engagement. Training@CarryTrainer.com or CarryTrainer.com.